later. Yes, recording in progress. Okay, wonderful. Thank you so much. Hello, everyone, and welcome to this virtual event brought to you by Kitchener Quantum Learning Hub. As you realize, our name changed. We removed the enthusiast part because we have some experts in. My name is Reza, and I'm thrilled to present to you our guest today, very special guest. We have Mr. William Hurley, and he goes by Whurley. If I'm pronouncing it wrong, he can correct me. Thanks. He's the founder and CEO of Strangeworks, along with some other startups that he has started. Whurley is an Eisenhower Fellow, a senior member of the Institute for Electrical and Electronic Engineering, IEEE, entrepreneur and investor, and he loves quantum computing. He is the author of the most famous book in quantum computing, The Quantum Computing for Babies, a highly recommended book to read. It's available on Amazon and everywhere else, so you can buy it there. So we love to hear your questions, comments, so please feel free to post them in the chat box. You can even unmute your mic and ask questions if you have. There will be a recorded version of this available later. I can post a link to it to where you can find it on comments about this event on the Meetup page. Now, okay, without any further ado, let's hear from the man of the hour, Mr. William Hurley. Thank you so much for joining us.
Well, thank you for having me. That is an insane intro. And for all of the quantum experts, like my friend John and others online, remember, I'm the software guy, not the physics guy. But I'm gonna do the best I can for what we're asked to do, which is basically give a high-level overview of kind of quantum and what it is, and some things you can do with it, maybe some places you can use it, and then answer a bunch of questions. And obviously, also, I was talked about a little bit about quantumcomputing.com and some of the resources that are free that you can go and play around with today and where they're going. So I believe you can see my screen okay. You just see a slide deck. Is that right? All right, perfect. Yes. So the number one thing everybody gets asked, and John, I'm going to start right out with it, is when is this coming? So pessimists think it's 20 years out. Optimists think it's 3 years out. Realists, should be preparing today. The reality is when is what coming? Is it we're exiting the NISQ era, which is this kind of noisy qubit era that we're in right now? Is it we're looking for fault tolerant machine? Is it just quantum computing becomes ubiquitous? Every time people talk about these questions publicly, there's a dozen ways to look at it, and we're all talking about it in different ways. I think the best way to look at it is there's work to be done in quantum computing today, and there are many jobs coming available today, and there are many people using it today. So if you're interested in quantum, you should be doing it today. Long story short. Now, of course, a lot of this all falls out of 1927, the Fifth Solvay Conference, when quantum mechanics kind of really came into being. There's a bunch of computer science that's happened since then, a bunch of information and quantum information theory to get us to where we are today, which in my opinion, this is the space race of our generation. I love artificial intelligence. I'm not anti-AI, but the fact is that in the 80s, when I was first messing with AI, what we defined as AI then is now a super intelligence, and the goalpost has moved and everything's kind of moved. And at the end of the day, if you think about it, I'm putting data in a computer, it's doing some inferencing, it's giving me an answer back out. It's kind of like, that's what I thought computers did, right? So, I mean, I love the dream of the singularity and all these other things, but I think that is maybe the only thing overhyped more than quantum right now these days. So again, the way I look at this, the way we look at this at Strangeworks is there was an industrial age, there was an information age, and there's a quantum age, right? That quantum mechanics is going to come into more things than just computing. It'll come into sensors and networking and all manner of things. And all of those things are even further left afield from the stuff that I do as a software engineer. But that's really, really exciting. I mean, there are so many opportunities. And when you think about, our view of the opportunity, I kind of think back to 1963. In 1963, you had a guy named Jack say, here's a thing called a microprocessor. And everybody thought that is going to make spreadsheets so much faster, right? And nobody was thinking about AI or autonomous vehicles or drones or any of these things. And so the way I'm looking at it is, at some point, we'll reach a point where quantum happens. I'm not interested in all the things quantum can be applied to today. I'm interested in the trillions of dollars in opportunity and all the new stuff that will come out of this technology becoming ubiquitous. So that's kind of the focal point, which is why if you go to our website, or a lot of people say, we're not really sure what Strangeworks does. It's because that's what we're doing. It's a very, very long-term plan for us. Now, there are so many people getting involved in this area, starting with countries. It is an arms race. When I say this, sometimes people get sensitive about it, say, well, is it? And it's like, yeah, I've met with many of the governments on this list, and they all believe that it'll either be the key to their national security, or it'll be the future of their economy, or part of the future of their economic development, along with AI and things like that. They're all rushing into this. And you're starting to see more and more countries, of the 193 countries in the UN, I think there's actually like 30 or 40 of them now that have some, even though it might be minor, investment in researching quantum. Now, a lot of that's around cryptography. There's no doubt. A lot of that's around communications, other things. But a great deal of it is computing. And really, at the end of the day, if you look at the DoD's latest proposal here in the States, they said we need to have quantum sensors that can have data communicated over a quantum network, can be run on a quantum computer, right? Whether that's right or wrong, it doesn't matter, but all those things are going to overlap. They're going to interchange at some point. So there's also a ton of companies that are already working in this. Earlier on that slide, I said, how would you approach this? Would you, think it's 20 years out? Would you think it's 3 years out? Is it today? Well, right now, today, all of the companies you see on this slide are actively doing things in quantum. And that doesn't mean these are the only companies. These are just ones that I've personally spoken to about what they're doing with quantum, right? And so there's a big, heavy focus in finance, obviously military applications, people like Northrop Grumman, Lockheed Martin, obviously, and Raytheon, obviously things like that use batteries. So battery research is big, Volkswagen, BMW, et cetera, Tesla rumored to now be looking to use quantum computing for battery research as well. And a ton of other stuff. Obviously, the banks, the consultancies, and the list goes on and on. So, is this a market like AI right now? We need more people trained and we can go get a job. Yes. Is it as big? No. And I've got another, kind of way to put that into focus. You're at the beginning of one of the biggest opportunities in computer science and physics in history, in my opinion. Period, right? Of course, I'm the software guy, so of course I think that, but I think this is going to be changed. So what is quantum? And so, got some really high level stuff. Again, not being a physicist, basically it's based on a qubit. Now, a lot of people like to take a coin. I've done this demo before. Tons of people have done it. Say you put in your palm, heads up, it's a 1, tails up, it's a 0. Binary system, it can only be one of those two things. We flip that coin in the air at the apex of that spin. Is it a 1 or a 0? It's in a superposition, not of 1 and 0 and everything in between, but of a probability of collapsing into a 1 or 0. So it's a two-level quantum mechanical system. It allows for superposition, and measuring that superposition gives us that probabilistic outcome. And basically, think of it like a soccer ball. Now, I usually have a lot of props, and someone, probably my wife, replaced my soccer ball with this 30-pound Death Star medicine ball. So apparently I need to hit a gym. But if you think of it as a ball, like a block sphere, it's pointing straight up, it's a 1, pointing straight down, it's a 0, but it can be oriented in any of those positions in between. Now, how do we do that? We change the axis of the X and the Y and the Z and so on and so forth. Why is this important? Why do we need this compute power? Well, you used to cross the United States by horse and buggy. It took weeks, months. It was a horrible trip. Maybe someone died. Maybe you had to eat somebody in your party. Who knows? It was not good news. Then we got the rail system. That same trip from New York to San Francisco took a week, okay? But no matter how far you go, eventually you reach an ocean. And we have oceans of complexity in the world, in material science and aerospace and all manner of areas. And so we need air travel. We need a plane. So quantum computers aren't here to replace classical computers, but they are here to augment them to do things we've never been able to do before. And, depending on who you are, different people for a while think, they're really pushed on the quantum computers. But the fact is, at the end of the day, We still have trains all over in the world. We have air travel. We're about to have supersonic air travel again, and we're about to have space travel, right? So just think of it as another target that you can task with things that your current computers can't do. So again, doesn't replace them, does augment them really well. And a good way to show that is by dissecting an actual quantum computing calculation. The one I've been using forever, for better or for worse, is Shor's algorithm, because everybody's heard of it and knows it. And if you think about it, we've got a quantum cloud coprocessor, and we've got a local processor. We have 5 steps. We only really have one that needs to be quantum. So, first thing we're going to do is we're going to say, if n's even, returns to, is it an even or odd number? Obviously, we could use an iPhone or shell script or anything to do all of these things, right? Is it a product of 2 coprimes, right? So sorry, go back here because I'm going, oops, didn't know if I went back. So I'm using 15, I forgot to say that. So then we want us to take a random number, make sure it's not a factor. So 7 is not a factor of 15. And then we want to find the order of R of X mod N, which is where the quantum, non-deterministic magic happens. When that happens, right, we get a return and we say, all right, let's check that. And if we got what we're looking for, we didn't. Now, what does that mean? Basically, that means 3 times 5 is 15 in that example we just gave, okay? But this is really, really important to understand. There are a ton of things that you need a classical computer for in quantum, for maybe managing the cryogenics or the lasers or all manner of things. But even in just doing the calculations, it'd be a waste in time and resource to run all 4 of those on a quantum machine in most cases. Now that'll change, prices will be commoditized, hardware will get commoditized, et cetera, et cetera. But another example is maybe looking at the power of a quantum algorithm is comparing a classical walk to a quantum walk. So classical walk's pretty simple. We're at the Austin FC game. We have a football team now, a real football team. Very happy about that. And we're at the game and everybody's wearing an Austin FC jersey. And Reza and John, I'm looking, John and I, we're looking for Reza. And everybody sitting at the bar looks the same from behind. And Reza's sitting right there. We don't know that, okay? So if you do a classical walk where we would walk up to a seat, flip a coin, if it's heads, we go to the right, if it's tails, we go to the left, right? That would lead us to basically kind of a bell curve, if you will, on a distribution on our search, meaning that we can go right and left a whole lot of times and still not find it, okay? That's because it distributes like this, right? It also means that we're not searching the entire space that we want, right? So again, it looks like a bell curve. We're searching within this probability density. But what if we had a quantum coin? What if we could flip a coin and go right and left at the same time, right? Then we'd search a larger problem space faster. It wouldn't look like that bell curve. It would look more like kind of a peaks on each end, right? Or, as I like to put it, looks a little more like vampire fangs, right? So we're able to do, what does that mean? Well, if you look at that spread on the right, and then you look at the spread on the left and you compare them, we're obviously we can search a lot more problem space in a lot less time. So explore more steps faster. And that's the power of things like Grover search algorithms and some of the other search algorithms in quantum. So continue on example, if you have an entrance and we're saying we got to get people out to the exit, and we do a classical, kind of goes like that. Quantum, we can go across all of those paths somewhat at the same time. This, like superposition, is often misconstrued. When I first started in quantum, everybody was like, superposition is it's a 1 and a 0 at the same time, or it can be everything in between. And then I started trying to program these things. I was like, okay, none of that is correct. But if we continue with that, then if we put a whole bunch of people in, right, then obviously we're going to get to answers. We're going to find our solution faster. Now, where can this be used? There's a ton of applications. I disagree with a lot of people out there that are focused on just chemistry or other areas. Those are obviously super promising areas. But I believe that what we're really looking for here as a computer scientist is evaluation times. So we have a set of problems, we increase the variables and the evaluation time skyrockets. Those are the kind of domain of quantum computing to me, or one of the potential domains. And so I'm not really focused on industry verticals or specific problem sets. I'm more focused on, Michelle Simmons uses the traveling salesperson example. I don't know if she does anymore. That example could be argued its validity. But in that, let's say Reza and John and I want to go to 14 cities, and we do it on my Mac laptop, and it takes about 1,600 seconds. But then we want to increase by only a factor of 8. And we're going to go to 22 cities. That same laptop could take 2,000 years, right? Increase to 28, it could be longer than time known universe. as she said, that's an example of that evaluation time soaring is we're not really adding big hunks of variables. So that leaves us with what Reza also asked me to talk about, which is what the hell do you guys do? So what are you doing? We do have two wonderful physicists, my chief science officer, Cedar Rodriguez Rosario, and my now business guy, Andrew Ochoa, because he had a PhD and he got here and he decided he needed an MBA as well. So now he has both because, has a penchant to be overeducated for some reason. And we started in this area completely new to it, right? I was just fascinated. When I get out on stage and I say, I really love this, I really think this is gonna be one of the biggest things to change the world. It's like, I believe it, right? And I invite, all the help and criticism and everything I can, because I'm not even at the level of a student of quantum mechanics. I barely say I'm a level of student of quantum computing. And I'll also tell you, the first thing I learned was these things aren't really computers. They're right now on the stage we're in. The physicists call it the NISC, this noisy intermediate kind of quantum madness we're dealing with. I think of them not as computers, but as really good lab equipment for exploring the quantum landscape. Because as a software developer, they're certainly not computers, right? They're hardly up and down. The time decoherence sets in. There's all manner of things that I've learned about in the 4 years we've been in the space. But we looked at it and we said, okay, what is the relationship between academia and industry throughout history, throughout technological changes? When do things go from advanced research to applied science? And how do we get it there? And then what happens after that? I remember in 1993, Stephen Mills, leader of IBM Software, asking me what the hell a web developer was. He's like, is that just a developer? And I was like, I don't know. And people were making 300, 400, 500,000 a year to code HTML because nobody knew how to do it. And then now it's $9 on the Wix site. I'm not saying quantum's going to go that far, but at some point for us to get it in the market, for us to get wide adoption, we're going to have to, because we don't have enough quantum programs turning out enough students to be a quantum workforce. So there's going to be this race between building up the workforce we need and building up the abstraction layers that take it broad. And, it's to be determined on what's going to happen on that. So we looked at it this way. We said, software engineers is really confusing. There's Qiskit and Q Sharp and Strawberry Fields and on and on and on and on and on. And then there were a bunch of access barriers, right? When we first started, we couldn't get access to a machine to play around with. There was a limited ecosystem at the time. All of this has changed over the last 4 years. Again, there was no workforce. When I talk to CIOs around the world, one of the first things they say is, well, why do I need a physicist? It's like, well, in the early days of computing, you used to have to be an electrical engineer to understand the flow of electricity between the gates to program a computer. Today, it really, you need to be a physicist. I mean, I'll tell you, or have a physicist on your team to be able to utilize one of the machines. And so that's where we're at. Now, eventually, as we go from advanced research to applied research, those physicists will be building, the next generations of computers, and electrical engineers and other people will be building machines and putting them out, et cetera, and these abstraction layers will come in. I believe that, that's could be a lot closer than we think. So we took all of that, we partnered with Stack Overflow, and we built a community that's now roughly around 17,000, 18,000 people. Enthusiasts, software developers, physicists, everybody. And we asked what they needed. And unfortunately, they didn't know what they needed. So we built something anyway. And what we built was quantumcomputing.com as a playground, kind of test bed for people to have a library of, different algorithms they could play with, have a GitHub-like feature where they can clone them, be able to run them on any of the simulators or any of the frameworks, be able to actually get out to quantum hardware. And now it's the actual only place that IBM machines are currently available outside of IBM, as well as roughly another couple dozen machines and simulators and things. So we've got stuff from Rigetti and IonQ and IQM, and Pascal is coming online soon, and Hitachi, and et cetera, et cetera. It's a good place. Think of it like a sandbox to play around with computing. And by the way, it won't be that forever, and it won't be there forever. This is, again, something we did to try to learn about it by pushing this out into our world of software developers. And it really picked up some steam. So we got a lot of people that joined what we call the Strangeworks Quantum Syndicate in hardware and software and consulting and in education. This is actually sadly outdated. There's a lot more than this. And all of those people started feeding back into what we're doing and improving it. So in March of 2022, we will turn 5 years old. So that means we'll have been doing this for 4 years. And when I hear physicists that have been doing this for 20 years, I'm like, how? Because it's really hard. Like total new respect for physics and physicists came out of the last 4 years, for sure. As the hackers and painters that were like, oh, we're just gonna go write some code and mess it all up. But this is a really strong thing. We like it a lot. A lot of people have used it. We haven't ever really published numbers, but tens of thousands of experiments have been run across it since February when it's been released. It's been hugely successful, but we've also found out it may not be the right tool for everybody, and there's a lot of other tooling that's still missing out of the quantum stack. Now, we don't intend, and we'll never go down into noise control and pulse control and things like that. It's not what we do, right? We're more of an integration, if you will, a compute fabric play. So quantum computing is just one piece of what we call exotic computing. So there'll be neuromorphic, anamorphic, there'll be biological-based computers, there'll be all these things. They're becoming at developers and enterprises faster and faster and faster. And the idea is to have a sandbox for all of these things where people can easily figure out what they might need, learn the skills to build it, and be able to deploy it within the enterprise. And we've actually going to make a pretty big change in March as to how some of this works based on the feedback we've got from these tens of thousands of people now. By the way, opening the floodgate on physics for all the startup fans out there, great idea, need that information. Also, terrible pain in the ass, cannot see the email my wife sends me that says print this or don't come home, because there's too many emails and too many texts and things like that. So we're going to go into questions here in a few minutes, but I wanted to kind of close up. One, anybody who asks questions, if they'll give their address to Reza and Reza sends me the address, I will send you a signed copy of Quantum Computing for Babies. He says very popular. It sold 35,000 copies, plus so far. The reality is it's probably the bane of physicists everywhere. They're like, really, this? But it started kind of as a joke with Chris Ferry, and I had no idea that in my world, in software world, everybody would be like, yeah, like it's like a reference manual, which is insane because it is literally written for babies. But that tells you a good deal about how educated software people are on quantum computing. I mean, we see thousands of people come in, play around, and leave, because eventually you got to know the physics. You're going to do teleportation. How are you going to debug it if you don't understand how teleportation works, right? How are you going to do some of these things? So again, being a physicist is super, super important. And the last thing I'd like to say is, I think that we live in the greatest time to be alive in history. I do believe that quantum mechanics coming into all these areas of our lives are going to create untold opportunities and untold fortunes and improve the human condition overall. Maybe, it's way overhyped. I gave a presentation last week at the Insight Quantum Conference in New York, and I had slides showing how much people search for everything else but quantum, right? It's kind of a flat line down at the bottom, and how much of the hype is affecting it. I had four things that looked like memes, except one of them was an actual news story title, not a meme. It had a picture of Doc Brown and said, "Scientists turn back time, with time crystals," or whatever. And it was like, yeah, I mean, sort of, right? And so, we really, really, I want to get all of you to join quantum, to be involved in quantum, but I want everybody to also work on a lot more collaboration, a lot less conflict, a lot less hype, more like real world stuff. I think of it as we're sitting in a kitchen and, Reza's got berries all over his face and the sprinklers raining down on John, and I'm trying to put out the fire on the stove, but we're all fighting for this piece of quantum pie that just doesn't exist yet. I mean, make no mistake, there is no quantum market. There's the beginnings of market. There is money being spent here and there in consulting and things like that, but we're not there yet. And when we get there, I don't know. I mean, could it be 5 years, 10 years? Sure. Could also be 2 years. I mean, I believe that as these number of qubits increase, brilliant physicists will use that to solve some of the problems with quantum mechanics and quantum physics and challenges. And I think we'll see an inflection point where we go from, very few qubits up. I mean, think about it. In 2012, MIT had like 7 or 12, whatever it was, Fast forward 2017, we went from 17 to 65 to 127, whatever. We know some of those weren't actual machines. There were people projecting a roadmap and getting PR off of it. But IBM's publicly placed a roadmap. They just released 127. They're about to release 433 next year, and then there'll be 1121. And even at IBM, they get to 1121 in 2024. In 2025, they're like, between 1,000 and 1,000,000. We don't know what all we're going to discover in those first 3 years. And of course, you have D-Wave saying they have 5,000. You have people, and that's the thing is like, we need nomenclature, we need standards, we need a way to discuss quantum computing from the same lens. This academic versus industry thing, that doesn't exist. We just need to admit there's some bad actors on each side. Academia and industry have worked together on 100 technology projects and brought them to market and changed all of our lives. And I don't think quantum is any more or less special from that type of lens. So with that, I think I said 25 minutes. We have 9, 8, 7, 6, 5, 4, 3, 2, 1. I will hand it over to Reza and we'll try to answer any questions that have came up.
Thank you. Thank you very much, Hurley. Well, we can, you can just unmute yourself and thanks for the great talk. It was so much information packed into 25 minutes. So I have lots of questions, Hurley, and I'm sure our audience too. You touched on very important points. I think that these and basically detangling the hype from the number of qubits and everything that we hear from the reality and what those qubits can do and when they can be useful, have some useful applications for us is very, very important, because a lot of it is kind of like more like on commercial side. And I love how you think about quantum computing as collaboration and a word that we can all collaborate from academia, startup, industry, and make something great for humanity. Wonderful. I like how you think about it. I think a question is, what is the correlation between those numbers of investment that you showed us and where different countries are standing in quantum tech world?
That's a great question. So money does not solve problems, whether it's a startup or the countries. I just gave this presentation in New York, and part of what I said, I know upset a lot of people, but you have all of this money flowing into these hardware companies, okay? And I'm not picking a winner, right? I'm Switzerland. I love them all. But if you think about it, there's a very famous book from 1971, the year I was born, called The Mythical Man Month. And I don't know if anybody's ever read it, but you should read it before you do software, because it was by a very famous engineer at IBM who noticed that when they added more people or more funding to a project that was behind, it actually got further and further and further behind, because you can't just be like $1 billion, now make 1,000 qubit machine, physicist, right? Like that's not how science works. And so, when I see this money flowing through, there's 2 or 3 things to keep in mind. Number one is, in the US, we have 1.2 billion in appropriations. It's a very key word, because appropriations means if I, as a government agency, can go find somewhere else in the budget to steal it from, I can then try to get it authorized. And after I have an authorization, then I have the money to distribute it. And I enter a whole nother cycle of ways that it funds. And every country is different. But for the most part, there's a lot of systems and controls when you're throwing around tax dollars. And so therefore, it's not like, oh, the US dedicated 1.2 billion, everybody go get some. I mean, it's going to take a while to figure all that out and where it's taken from, et cetera, et cetera. Now, on the company side, I think money kills startups. I think you cannot build a culture overnight. We have hired 14 people in 4 years, right? So we're averaging a few people a year, and we'll continue to do that for the foreseeable future, probably for the next 2 years at least. The reason is that hardware is hard. Software is also hard. Building teams to work together cohesively isn't taking a list of resumes and skills and saying like, great, smash them up, give them the money, now they work together. It's much more, and you already see this, right? You just saw Justin Jing and Denise, both leave their companies and join Atom Computing. not the first time you've seen either one of them leave a company, won't be the last. And there's a whole bunch of other people that moved around. Dave Bacon was at IonQ, now he's back at Google, right? So you're going to see all of this move around. Part of this is going to be a frustration with culture. Culture will be a killer for quantum startups. There'll be the industry versus academia culture where somebody coming from academia very legitimately is like, hey, we've got money, we want to do a thing. Here's how we lay it out in our research project. The science can take time. And you can have the startup people that are like, you know what, just put duct tape on that and we ship it. And if it breaks, right, the Zuckerbergs or Michael Dells of quantum will definitely appear where they're like, you know, I remember Michael Dell used to have the computers in the back of his pickup at UT, and he would just ship them. And some of them would be broken. He knew, you know, says he did, but you know, when they shipped out, and he'd just be like, great, we'll just replace that one, right? They're just floating stuff. So there's this kind of like break it fast stuff and this kind of like very metered, measured approach to science. They don't have to conflict, but they're going to in a lot of these startups. And so whether it's the countries, whether it's startups or wherever, I don't think that a lot of money is a good thing. I think you need just enough money and just enough team. And what we need is time. You cannot rush the science of this. You cannot rush the market. Adding billions of dollars into it doesn't mean it's going to make a market. I know Silicon Valley's done that a few times, and I know that they're trying to do it again with quantum, but quantum, you know, it's real science, so it's not going to work that way.
Oh, I see. Wonderful. Okay,
John, you can't ask questions. No, I'm just kidding. John's got his hand raised. Just kidding.